Hello, my name is Jin, and I'm a fourth year student at the University of Oxford reading Engineering Science. I've made a video of my experience as a participant of the Google Summer of Codes program. I hope you enjoy this video. Today I'm going to talk about my experience as a student developer for OpenCV as part of the Google Summer of Codes program. My initial proposal entailed a research on the tracker proposed an accurate tracking by overlapping maximization by Deneligen et al. After some discussions with the mentors, I came to realize that there were some problems associated with implementing this particular tracker. Firstly, there were some issues regarding the license, such that it would be inappropriate to add the tracker to the OpenCV library. Secondly, the tracker required implementation of custom layers that were specific to CUDA. This meant that we switched our focus to SiamRPN++ tracker, proposed an evolution of CME's visual tracking with very deep networks. Implementing this type of tracker resolved the license issues, and we thought that it was an ideal tracker to implement given a strong performance over the other state-of-the-visual trackers on TrackingNet dataset. It achieved area under the characteristic curve score of 73.3% and precision of 69.4%. A CME's network in general refers to a network within a specific structure, one that consists of identical neural networks that use shared weights. Given a candidate image X and an exemplar image Z, the aim is to learn a function that compares X and Z and return a high score if the two images depict the same image and a low score otherwise. The presence of the depthwise cross-correlation layer is a feat specific to this particular visual tracker. With reference to the paper, the cross-correlation is an operation used to embed information coming from the two branches. The original cross-correlation layer is used in SiamFC to obtain a single channel response map as shown in the figure. SiamRPN++ performs depthwise cross-correlation by obtaining adjusted feature maps from each of the search branch and the target branch. The two feature maps, each respective from these branches, with the same number of channels, perform correlation operation channel by channel. For the export of the torch model to ONNX model, the tracker was effectively divided into three parts: the backbone network ResNet 50, the adjusted layers, and the multiple depthwise regional proposal networks. To briefly touch upon what ONNX is, the acronym stands for Open Neural Network Exchange, which is an open source platform that allows interoperability between different machine learning frameworks such as PyTorch, TensorFlow, and Keras. In the context of this project, the Torch implementation of SiamRPN++ was exported to ONNX such that it is later imported using OpenCV library. There were, however, Torch operators not currently supported by ONNX. This meant that some of the operators had to be redefined in terms of relatively more elementary functions which were currently supported by ONNX. Whilst it was possible to implement some layers using Torch's JITscript method, which accommodates dynamic layers, it was a less preferable option, given that the usage of such custom layer would mean we had to adjust OpenCV's ONNX importer such that it can import such layer. There were also problems associated with the conditional functions and loop functions. With regards to the problem related to the former, different ONNX models had to be generated for each of the conditional. Therefore, it was important to rid any unnecessary conditionals, and in certain cases, the values had to be hard-coded where necessary. The export of Torch to ONNX format prevented any repetition over the size or shape of a given tensor. More generally, there were also cases where the loop itself was preventing a conversion to ONNX format. In order to resolve these issues, the data structure of some of the variables related to a tensor had to be converted to other format, and in a few cases, the loops had to be coded in a long-winded way so that the conversion was successful. Having successfully exported each part of the visual tracker model to ONNX, we then attempted to import the ONNX models using the OpenCV library. When importing the converted ONNX file of the visual tracker model, the team faced a few problems. One of the problems was that when importing the multi-RPM model, the ONNX importer at this stage did not support inconstant weights for convolutions. Specifically, the convolution did not support variable kernel or bias for the convolution. I would like to thank one of my mentors, Lyubov, for her pull request, which provided support for such convolution. The successful export and import of the model finally meant that I was able to complete my pull request, which was essentially about having the SiamRPN++ tracker sample in the OpenCV repository, With the revisions of the codes by the mentors, I was able to contribute to the library by adding the SiamRPN++ Python file, the details of which can be found in the pull request shown. Sample videos of visual tracking with SiamRPN++ will now be shown, and for more sample videos, please refer to the Google Drive link. To conclude, I would like to thank my mentors Lyubov, Ilya and Stefano for the wonderful supervision, and I would also like to thank the OpenCV team for this opportunity. Thank you.